Hello guys, welcome to Backbencher Studies channel. In the last video, we have discussed some of the time domain specifications of the second order system. We discussed what we call it as a rise time and what is peak time and what is peak overshoot and what is settling time. So let us derive all of these with the help of this equation which we have derived in the last two classes. So what is rise time? So let us start with this rise time. So what is rise time? We already discussed that the time required to reach this steady state value, which is equal to 1 for the first time. So we saw the response of the second order system, which is the unit step response of the second order system, which is gradually reaching to 1 with an oscillatory behavior. That we have saw that. So this is the input we have given, that is the value of 1. So so this is kind of like a exponentially varying sinusoidal signal which is continuously oscillating about this steady state value. We saw that these type of response we arrived at. So the time which is required from in the starting stage to reaching this steady state value is what is called as rise time. So that is being shown over here. So if we see that this is the steady state value, and so this is the time axis, the time values of time we have. So here we have t equal to 0 and here we have t equal to t rise time. So with in this width we have this rise time. So and this is the y-axis which is depicted as the output c of t, which we are using as a convention for the output. So let us derive this rise time. So if we place this c of t as 1, then we can at t equal to tr, then we can derive this tr over here just like that. So this is the output we derived in the last classes. That is the output. The c of t is equal to 1 minus exponential del minus del omega n by square root of 1 minus delta square into sine of omega dt plus theta. This omega d, we already derived that omega d is equal to omega n into root of 1 minus delta square. So this is how we derived this formula. We arrived at this formula. If we place t equal to t2 over here, that is the rise time over here, then we can have the c of t value as 1 over here. So if we equate that to 1, so 1 is equal to, if we place t equal to t2 in this equation, then we have this expression over here. So if we equate this, if we cancel this one on both sides, then we are left with this expression being equal to 0. So this exponential, as this exponential cannot be 0, we can equate this sinusoidal term over here as 0. And we know that a sinusoid will be equal to 0 for any value, any multiple of pi. So for the but so this is being depicted in the following figure. So it is reaching 1 for the first time and 1 for the second time, and then if it is encouraged to do that, it will cross n number of times. So here we have n over here, but we are calculating for rise time, that is for the first time. So we place n equal to 1 over here. So if we find out this value of rise time t2, which is called which will be obtained from this equation as pi minus theta by omega d. So we already derived that omega d is equal to omega n into root of 1 minus delta square. So the rise time will depend on the inversely proportional to the natural frequency of the system. So this is how we can derive the rise time of the system. So if you learn something new in this lecture, please do like this video. And if you are new to our channel, please do subscribe to our channel. Thank you guys.